Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve truss using Salome FEA. So we'll be modeling this using a beam element, a 1D element, and we'll apply a load here of 200 kN, and here we are going to fix it. So the material property of this beam is steel, and we are going to do linear static analysis. So first go to open Salome FEA. Salome FEA is the wonderful open source software for finite element analysis. Now just go into geometry model. It is similar to ANSYS. So now just see the model. First, what we want to do is we just want to make a points, every points using vertex. Then we'll create a line. We'll join the lines using points. We'll join the points using lines. So first, the first point I just want to make it 0, 0. So here you can go for it. Basic points. First point 0, 0. The next point is x is 0, y is 4, apply, and third point I will make it y is 0 and x is 4. Here you can keep it this one. X is 4, apply, and we'll go for this point y is 2 and x is 4. See, it's coming here, right? Then next point I just want to make this one, x is 8, y is 2. Apply and close. Now I have created all the points. Then I will make line using these points. Go to basic line. Here also we can take it line. So first I will connect this line. So this point to this point, apply. Then from here to here, apply. Then this point to this point, right? Then you just want to select this point, then this point, apply. We'll add the axis, then we'll get into. Then we can go for this point, apply it. Then finally we just want to connect these two lines. So from this point to this point, apply. Then this point to this point, apply and close. This is our model actually. See, this is our model. So now we can switch on this. We have modeled in XY plane. Now we can make these all the lines into single. So press the shift and select all the lines and go to new entity. There is an option called build, choose wire. So this is a wire. We can name it, this one is as truss, and apply and close. Now I have created this wire. Now we have completed our model. Then we can go for creating groups for applying the boundary tension. Create group. First we will create edge groups. Select all. All the edges are truss. So I'm just naming this into truss. Apply. Then I just want to fix this complete edge. So for that, this edge, add. I just want to fix it. Apply it. Then I just want to apply a load of 200 kN up this point. Just click this point. For that, go for vertex, select this point, add, make this group as a load. Now apply and close. Now we have we have created truss, fix, load. Now we can save this file. Go for file, save as, pictures, code aster, Truss, first case, saving here. So now complete modeling and creating groups are done. Now we can go for meshing. So mesh, create mesh, select this truss. Here 1D is enabled, remaining 3s are disabled because our model is 1D. Go for wire discretization, choose local length. So I'm just giving 0.2, OK, apply and close. Right click, compute. Now totally 139 edges and 137 nodes are created. Now this is our model. Now meshing also done. Just have a look. The groups are taken into the mesh. Yes. Now we can go for code aster. There are two ways we can generate a command file. One is we can use aster study. Another one is we can use efficient to generate the command file. In both way we can do. In first case, I will show you how to generate a command file using efficient. So now just export this mesh one. Export MED format. So I'm just exporting this here. Save it. Now mesh is done. Now we will generate a command file using efficient software. Just right click, open with OpenJDK Java 8 runtime. So first one is analysis type. Now we have to choose beam. Choose beam. Now model definition is done. Now go to material. So our material is carbon steel. So Young's modulus is 210 e power 9. Poisson ratio is 0.3. Density is actually not required, but anyway I'm just specifying density. And assign to all. We can give all means it will take OUI. So it's done. Material definition and assigning are done. Now we can go for element type. It is a beam element and rectangle cross section. So assign to Truss. So this is the name I have given. We can have a look. So our element group is TRUSS. So Truss. This for that only I have created this group. Then go here. So these two thickness. Our model is not a hollow section. Our model is solid section as a rectangular section. I'm just giving 0.1. Now just add it. Now element property also now we have defined. Now we just want to define the boundary condition. So just go to, there are two. One is mesh group, another one is node group. So ours is, just have a look here. The fix is the edge group. Edge group is nothing but a mesh group. We can go for DDL, this one, mesh group. So we have to fix it. Fixed, and any name we can give it here. But is assigned to what is group name. So that name is to be correct name. Whatever we are given here, that is fix. Then we have to fix all the degree of freedom. 3 translation and 3 rotational degree of freedom. If you are using a solid element, we need not to define rotational degree of freedom, but beam element and shell element having rotational degree of freedom. So we have to arrest it. Now we have fixed it. Now what we want to do, we want to apply load. For that just go to load. Here just choose force on the node. Now I'm just defining as load. Assigned to the group name is also node. Load. So I want to apply, just have a look the direction. In y direction I just want to apply in negative y direction. So in y the load value is 200 kilonewton. So minus 200 kilonewton. We have to apply force in the Newton. So into 1000. 1230 I have added. Just add it. Now we have done. Now we can go for output. So we will save all the results. We want to see the reaction force, stresses, everything. So displacement, everything. So I'm just add all. Save the command file. So I'm just saving the file. This is static.com. Save it. Now the output file is saved. Now we can exit the wizard, efficient wizard. So now we have created geometry, we have created a mesh, and we have created command file also. So this is our command file, static. Just open the command file. Now you see, so the command has created. So debug is nothing but in French it's to start. So read mesh, define the model. Our model is so define model is this one. So is a PODT. This is Timosiki beam element. So then element property we have defined is a rectangular section, and the material it's there, and we are assigning the material here. Then finally we are applying the fixed boundary condition and load. So this is the solver, you can see it, meca static is the solver. So then we are calculating other values. The solver will calculate only displacement, the primary variable. The remaining variable, stress, strain, everything are secondary variable that has to be derived from the displacement. Then we are saving the results. This is result command. Then finally we are finishing. So then we'll run this mesh and command file using Salome FEA ASDK. Now go to tools, plugins, code aster, run ASDK. This is actually code aster ASDK. So this is actually path. Choose the path. So pictures, code aster, truss. My case is first one. Save it. This is a folder I have chosen. Then 6 file we have to generate. So first one, initial one is command file. The next one is mesh file. These are output file, message, resu, error. These are output file. Finally RMD file. This is a result file. We want to see the results in paraview, means we have to save the results in RMD format. So first, so we'll keep the folder on the left side to avoid error in naming. So first one is static .comm. Next one is mesh file, mesh _1 .med. Then message file. This is, we can give any name. I'm just giving message.mess. Then resu. Same name I'm giving. Error.err. Then result.rmd. So here we can specify memory, how much you want to use. I just want to use 2 GB. Is much more enough for solving a simple problem. So interactive follow-up, you just tick this one. Then finally we need to save this file. Go to file, save. So I'm just giving simple name, just ASDK, save it. Now I have saved everything. Now we can run this file. Just go to run. So here you can see if any error comes, the error message will come here. So no error. And message file also you can open and check. Here you can see there is alarm but no error. Now it has solved. Now we can see the results in paraview. So you just have a look here, there is a result file. See, so the memory is 105.2 KB. Now we will open this result.rmd file in paraview and we will see the results. So just go to paraview, open. We just want to choose our RMD file. This one is our output file, RMD. Just open it. So just apply it. This is our model. Just see. Now we can go for displacement. So this is actually a displacement. So if you want to change the color pattern in color palette, just change this into rainbow, blue to red, apply, close. Here just choose the 13 to 12. So this one is the displacement plot. If you want to see a deformed shape of this displacement, just go, there is an option called generate vectors. Just tick this one, apply it. Now here you can see wrap y vector. Just click this one. So don't give this much scaling factor, just giving 50%, apply it. See, this is the way it will get deformed. So if you want to animate it, you just click it here, create new animation, single ramp. I just want to see it in 20 frames, save OK. Now we can use these play buttons to animate it. I'm just going back, making loop, I'm just playing. So we are just applying the load in y direction, downward y direction. That's why it's bending like this. So similarly we can see the reaction force. So there is a option called reaction at node. Just choose this one. So you see we are fixing here, so that's why we are getting reactions here. So vectors, reaction force vectors, it has only directions, only 3 direction. The reaction force in x direction, y direction, z direction. So we are applying force, so we'll be having 2 directional vectors. So if you want to see dx, so this is a dx here. So if you want to see the value here, so go to view, selection display inspector. There is an option called selection display inspector. Just tick this one and just scroll down here. So now we can go for selection. Here there is an option called node selection, selection point. So choose this one, select this point. Points label, we can choose vector. Yes. So how many nodes you are choosing, that values it will show here. So this is the force, reaction force in x, reaction force in y, and reaction force is z is 0. So here the reaction forces are all are 0 because we are not fixing any command here. So only here only we will get. Similarly we can see y value, z value. So that's all we are seeing. If you want to hide it, just click this one. Similarly I'm just giving fit screen. Now we can go for stress. This is a normal stress. So this is normal stress in the every bar, every beam. So now we can go for same way. Any point we can choose. I'm just choosing these 2. Here the stresses are 0. Here just have a look once. Now we have to choose here, label as which one you are choosing, whatever you are selecting, that only it will show. So this is the stress, sigma x, first one. This is the first value. This is sigma x. So everywhere we can see the stress if you select the value. This is this sigma value. Sigma x is a bending force. That is the way we can see. So in this tutorial we have seen this truss analysis in finite element analysis, truss in finite element analysis. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.